Aloha, everyone. Thank you for joining this launch. We are thrilled to show you something that we've been working on for years, literally, and thinking about for decades, and put a lot of effort into. It's still a work in progress, but we feel that it has reached a point where it is a useful resource, and we want to get it out there for people to use and get some feedback to us. So I'll just launch right in. Let's see. Okay, before I get started, a little bit of housekeeping. If you have any questions, please post them in the chat. We will have a break fairly soon. We'll have a chance to answer questions at that time. I want to ask everyone to please turn their cameras off until we get to the break, just to save on bandwidth. We have quite a few people on this call, over 160 at the moment, 165. If you know the URL to the portal, please do not access it right now. Don't access the portal until after the demo. If you don't know the URL to the portal, that's good. And we will provide it to you after the demo, and everybody can have a look, and you can play with it to your heart's content at that point. Okay, so the agenda for today will be a series of short presentations. I'll start off. Ryan Longman will go next and show you some website features. Jared McLean will talk about the portal itself, how you can access data and maps and so forth. Keri Kamelamela will talk about the cultural resources part of the portal. Then we'll have a break, followed by presentations by Matt Lucas, Keri Kodama, Abby Frazier, Sean Cleveland, and Michael Dodge. And I think Sean is actually going to present Michael's section there. So, and we'll have some questions then at the end, and hopefully we'll stay on time. I also want to call your attention to the organizations that are associated with the recent part of this effort, East West Center, Hawaiʻi EPSCoR, NSF, of which the Hawaiʻi EPSCoR is part of, Ikiwai project or program, which is the most recent Hawaiʻi EPSCoR project, and my organization, Water Resources Research Center at the University of Hawaii at Mānoa. Just to expand that list of folks involved just a little bit more, and showing everyone grouped by their, their position groups here, the climate scientists and Amy, very important for us, communications, the data and cyber infrastructure folks, data scientists and cyber infrastructure folks, really essential to this effort. And some of the many people who have contributed data to this are shown. Some of the important ones have recently helped us out a lot. And then Katie is there, as well as Noe for the cultural resources section. Those are just a few of the many, really dozens and dozens, or I'm not even sure, it might be in the hundreds of people who have contributed in one way or another to what we're now launching. And so I'm just showing a partial list of those here. This is just the top part of the list. I'm not going to go through all the names. We don't have time for that, unfortunately. But I'm just scrolling down the list just to give you an idea of how many people have contributed to this effort that we're now trying to make available to everyone. And I want to thank all of those people and others who have been instrumental in this effort. So how did we get here? Where does it start? The story really starts with the first Hawaiians. Native Hawaiians have always been keen observers of nature, and that includes weather and climate. We know from Hawaiian oral histories that are passed down in Oli and Mele, the chants and songs, because they're replete with references to winds, clouds, fog, and rain. And that's supported by the Olelo, the Hawaiian language, which is very detailed and refined in terms for weather events, weather processes, including, again, different winds, clouds, fog, and rain. And it's very place specific and shows a lot of knowledge. So Hawaiians really understood these weather processes. They understood the distribution of rainfall and temperature and moisture in their environment. And this was essential to their livelihoods. They understood how things change seasonally, and they understood that there were extreme events. And this is easy to see from the oral histories and the language. The first known measurements of rainfall that were, quantitative measurements were taken by Dr. Thomas Rook, who was a physician, a British physician who had immigrated to Hawaii. And he made those measurements in 1837 at his home at the corner of Nuuanu Avenue and Beretania Street. Soon others began making measurements as well. And not too long later, well, quite a few years later, by the end of that century, by 1900, over 100 stations were measuring rainfall in Hawaii. By that time, large-scale agriculture had begun with irrigated sugarcane. And as a result, there was a lot more interest and sort of institutional interest in rainfall and climate in general. And those companies, the sugar and the pineapple companies, greatly expanded the rainfall monitoring, and which reached over 400 stations by 1920 and peaked at over 1,000 stations in 1968, which was kind of at the peak of the sugar and pineapple plantation era. Thereafter, there were sharp declines in the number of stations, as you can see in the graph in the lower right. So over the decades, we really want to acknowledge that thousands of individuals have contributed to the climate database that we now present to you and that we treasure so much. Thousands of people from many walks of life. People worked in agriculture, in big agricultural companies, individual farmers, people worked in water utilities, many, many different agencies, USGS, federal agencies, and state and county agencies. And we're grateful to all of those folks, many who remain nameless, but they have contributed to this database in very important ways. So as data accumulated, eventually people started to make maps of rainfall, the patterns of rainfall. One of the earliest ones was done by Halstead and Luna Leopold in 1948, set of maps. Soon thereafter, Morty and Saul Price made a new map of Oahu rainfall. And then Bill Tollifer at the end of the 1950s developed a very comprehensive report with maps of mean and median rainfall for each island, annual and monthly. It's a big report with tables of data and so forth, really important landmark. Quite a few years later, Bernie Meisner in meteorology department here at UH developed a new set of median annual maps. And then soon thereafter, we got involved when in 1986, we put out the first Rainfall Atlas Hawaii, which was a paper report with, black lines on white paper kind of maps, but it was widely used and very helpful, we think, over the years. Chris Daly at Oregon State University's PRISM group did a set of maps for Hawaii in 2006, and these were digital online maps. And then we followed up and published in 2013 the newer, the revised Rainfall Atlas Hawaii, which is available online and is a high spatial resolution set of maps of mean, monthly, and annual rainfall. One of the things about all those maps that I showed is that they're all averages. They're all climatology. They don't give any information about the year-to-year difference or the difference from month to month of individual years, specific years. And so the next step really started with Abby Frazier, who did a set of maps of individual month-year maps from 1920, I think originally to 2008 in her master's thesis, and then published a set from 1920 to 2012 in 2006. So these are individual maps of each month, statewide, high resolution, and so forth. Ryan Longman then went ahead and did a set of daily rainfall maps. So every day from January 1st, 1990 to December 31st, 2014. So 25 years of daily maps, something like 9,000 maps, high resolution statewide individual daily rainfall maps. And Matt Lucas, part of our current team, just recently completed a set up through 2019, and now we have that connected to the present, as you'll see. So the Hawai'i Climate Data Portal is where we're at now. We've moved from just having a bit of data and mean maps now to having up-to-date maps, as you'll see. So why do we need a data portal? Why do we need a Hawai'i Climate Data Portal? I think everybody that's signed up here, and right now there are 176 people listening, all of you are interested in climate data, and that kind of shows why this is important. We need data for many things. Fill in the blank. It could be for resource management, water resources, or ecosystem resource management, for managing agriculture, for monitoring drought, for assessing flood hazard, or fire risk, many, many, many things that depend on these climate data. And then research, almost any kind of research you can think of has connections to climate and a need for climate data, very specific data for certain places and times. And so there is a need there, and there's a lot of data out there, but how can I get it? We're the experts, and we know how hard it is. It's hard for us. And so we realize it's very difficult. And many people doing research, for example, end up taking a big portion of their research time and effort put into the preliminary job of just getting the data they need for the climate before they start doing research on whatever it is. These data come in many different formats, so if you can find it, it's still very difficult to work with, it's difficult to compile. And then you may get through all that and find that there's no station at the location where I need information. And so we need maps that interpolate those data to any location and provide that information, make it easy to get. And it turns out the existing maps, at least until now, are not up to date. They are, all those individual month, year maps and daily maps that I showed you all had an end date. And so by the time the project's over, the most recent map is already old and there's no up-to-date maps. And that was the state of this, the situation at the time we began working on this, was to figure out a way to make these maps automatically updated and data automatically updated so that we always have it when we need it. Okay, before I turn this over to Ryan, I just wanted to mention a parallel project that we call the Hawaii Mesonet. So we have, for a long time, starting in the 80s, my group has done measurements in addition to doing the data analysis and compilation of the data. And we currently have 21 stations operating in Hawaii. It began on Haleakala on Maui with HaleNet in June 1988, and we still operate those stations, some of which are shown here. We also have stations in a network on the Big Island called HibNet. And we have 2 flex towers in Hawaii Volcanoes National Park, which we call HavoNet. We have 3 stations on Oahu. This year, or in the past year, in the past 12 months, we have been awarded 4 pretty good-sized grants that give us the funding, finally, to build out a statewide network of stations. So we'll be adding about 95 stations to our current 21 stations and operating this network in perpetuity. So these stations will measure a wide range of variables with very high-end equipment, and both above ground and below ground, and we'll record data every 5 minutes and transmit that data to us and get into the portal every 15 minutes. So we envision the Hawaii Mesonet as being the backbone of the network that provides data to the Hawaii Climate Data Portal in the future. So let's take a look inside the portal. And for that, I'm going to turn it over to Ryan Longman.
Aloha, everyone. Thank you for being here today. It's been an absolute monumental effort to get here. So the fact to see so many folks that showed up to support us, I just want to send a big mahalo Really a pleasure to be presenting this after so long of putting our heads down and getting it to where it needs to be. So I'm going to start with a question of what is the HCDP? And I think there's a lot of answers to this. And I can tell you when we started this, it was a place to get climate data. And we've been talking about this for over a decade. I've been working with Tom for over a decade, and we've been discussing how we could do this, put the data in a centralized place so folks could get it so they wouldn't have to recreate the same steps over and over again. And that's how we started out with this. And then as we started digging in, we realized that it wasn't just about data, it was about information. A lot of the tools and resources we were coming across, we realized how siloed they were and how folks didn't really know a lot of stuff that was out there. And we didn't know a lot of stuff that was out there either. So we thought that we could in simultaneously gather the data and put it in a way where we could easily disseminate it. But we could also gather information for folks. So it's a place to get climate data and information. It's a tool that allows us to explore the past, monitor the present, and project the future, especially given that we have these near real-time products like temperature and rainfall maps. It's also a portal to other places and data sources. And I'll reiterate this point. Not all of the data in Hawaii is in the portal. If you can't get the data there, we want to be able to direct you to where those spots are. So it's a portal in its true sense. If you go there and if the stuff is not there, you get to where you need to go. And maintaining that fluid aspect is something that's really important to us. And then finally, it's an opportunity to learn, to educate, to network, and share. We're creating ways where users can interact with the portal. They can contribute where it can benefit a really broad range of folks, from researchers to students to stakeholders to community members. And I'll be talking about some of that as we go along here. When you go onto the portal homepage, which Tom asked you not to do just yet, but you will be able to soon. You'll see a few things. This window right here, you'll see there's 4 dots there. It cycles through our monthly rainfall. So monthly rainfall is created on the first day of the month for the previous month. And then we have daily temperature, which is created minimum, maximum, and mean temperature, which is created the day after the last full day. So you'll see the map cycling through there, looking at real-time data. It's really state of the art in terms of this product. You also see some quick links to the data access tool that Jared will be demoing. Little information on the Mesonet, which will eventually be the Mesonet site itself once that's up and going. And then easy access to some of these other resources. And that's one of the designs here is to not be flashy, just to keep it simple and keep it clear and be able to get from one point to another with relative ease. So I'm going to walk folks through some of the features here. On our About page, you can just meet the team. Some of the history that Tom was describing. We have a little bit more in-depth history on the page, a little history of the HCDP itself, mapping, a little bit about the different monitoring networks that Tom touched on, and then an acknowledgement list that's really just scratching the surface on the people that contributed. And we put that together in the last week. And if there's a name or something you think needs to be on there, then please let us know. We're happy to update that and give people the acknowledgement they need. And this is for folks that really have contributed to this greater effort. Also on the HCDP, we have a library of resources. This includes at least 400 peer-reviewed journal articles and reports, all based around Hawaii-specific ecology or climate. So if it's not Hawaii-specific, it's really not there. We also have 31 years of National Weather Service monthly summaries. And I think that if you're on that list, Kevin Kodama from the National Weather Service puts out this list puts out a report every month, and it's comprehensive. It describes what happened the past month, and it's really an incredible resource. But they're only available on the National Weather Service for the last 12 months. So Kevin was kind enough to send us all of the historical ones, and we've got them in the PDF form, and they're on there as well. And I've utilized them in the past for research projects and for Hurricane Lane project and things that various research. It's a really incredible resource, and now it's available just with a quick download. We have using a Zotero plugin with the portal, so all of the information is searchable. I'm typed in rainfall here. I get all the articles that are related to rainfall, and then on each of these individual articles, you can actually get the download if it's an open source PDF, or you can actually, if it's not open source, you can link to the site and then use your credentials or whatever to get access to PDF. So that's making that information even more readily available. In terms of research, we are doing something called a research highlight. And we're asking folks to contribute to this, where we're highlighting past and ongoing research in the state. And we have a little system set up with it's a simple Google form where you can populate it with as much information as you want. This could be 10 pages long or 1 page or 1 paragraph. And the idea here is to connect folks with each other, to learn about research that's going on. And then in these individual sites, you can customize them, link to your publication. You can link to a website or another report, or you can put your social media or your LinkedIn or whatever you want, however you want to populate these. And then folks can leave comments on these as well. And then we're in the process of tagging them all. So we have about 30 in there now. We've used brute force to get those 30. And hopefully after this call, some folks will be interested in contributing some more. And we'll continue our brute force tactics to try to get this information in there. But again, you can just hit one of the tags and find that information and really connect with other researchers. We also are providing links to external resources. So a little paragraph, a little snippet, and then the actual link. So if you're, want to find something really fast and you don't want to look online for it, and you got the HCDP bookmarked, you can just click on these links and get to those places through the research portion of the portal as well. And if you're on the call and you're from an organization that's not listed, not here on the slide, but on the main page, please let us know and we can be happy to get your information up there. Climate tools. So the climate tools right now, we're linking to existing tools, the Rainfall Atlas from Chip Fletcher's lab, the Sea Level Rise Viewer and Coastal Erosion Tool, and the USGS Groundwater Recharge Tool. So these are tools that are already in existence. And then what I found in my work is that not a lot of folks, not a lot, but some folks are just not aware of these tools. So the portal just provides quick access to these things. And even for myself personally, they asked me the other day, there was a good product on sea level rise, and I basically was able just to go, I have a portal bookmarked, I grabbed the link, I send it right away. So it's really convenient to have access to these things that easy. And then we have a bunch of other tools that are currently under development right now, and I'll talk about them more in a bit, but they'll also be available through the tools page as well. In terms of the data portal itself, so Jared is going to give everybody a demo of this. It's really excited for him to show you. But in terms of the products that are going to be there, so right now we have 102 years of monthly rainfall data and maps. So again, from Abby Fraser's earlier effort from 1920 to 2016, and then Matt Lucas's recent effort, we have about 1,224 rainfall maps, and you can visualize those or download them. And then we have 32 years of monthly and daily temperature, minimum, maximum, mean, and minimum. And then again, there's about 35,139 maps as of today. So and there'll be 3 more tomorrow. So that's how fast the data is accumulating. And then this spring, we'll have the future climate projections of rainfall and temperature that are already out there, but we'll have them easily accessible. Abby Fraser at the second half of this presentation will talk to you about those products. And then we'll also have 32 years of daily solar radiation, relative humidity, and wind speed data. And that's a low-hanging fruit. And then in the summer, fall, we're going to move into daily rainfall mapping. We already have a method for that. Daily relative humidity, solar radiation, and wind speed maps. So gridded maps of all of these, potentially from 1990 to present day. And we have some feet on the ground doing work on that front. NDVI, so vegetation maps. Somebody's working on that now as well. That's going to be available. And then fire risk maps for a project we're working on with the Hawaii Emergency Management Agency. So another real-time tool, but we'll also have historical maps of that as well. So lots of data there now, but also lots of things on the horizon. And I'm literally just scratching the surface. I'm only talking about the fall now, but really, if you think about the portal and how it could move forward in the future, there's really an unlimited amount of resources and data that can be put in there. Now, I want to walk folks through what it looks like to make a map on the portal and why this is so unique. I think it's really important to highlight this. So what we do to make a monthly rainfall map is we query all of the data that's available through these electronic repositories. Some of them are nationally maintained. Some of them are really easily public accessible, like easy front-facing things. Other things are really got to go in a back door and find the links. And then we also have these local networks that really not everyone's is aware of. Some of them we just have the links to ourselves because we haven't been able to put them out on a public server. So we get that data through a coding syntax, and then we run it through this process. Tom kind of touched on this. We standardize it. We put it in the same time step, the same units, and we use a machine learning technique to flag these outliers. Really, when potentially a clogged rain gauge or a broken rain gauge or something like that. We try to find the values that are bad. We do a proven gap filling method on the daily time step. We aggregate to monthly, and then we do the spatial interpolation, which is just a fancy way for saying make a map. So then we make a map and we call that our preliminary product. So on March 1st, we make the February map with whatever data is available. And then that gets pushed to the portal. We have the map available, the gridded data that went into it, and then some uncertainty products. So where the map may have performed best or underperformed based on some metrics. And then data comes in. We call this latent data. There's like a lag on the data. So some folks don't report their data right away. It's not there on the first. It's potential that we have to go get the data out in the field, potentially even by a helicopter for some of these sites. So it's not always there on day one. Once we get all that latent data, we run it through the same process and we produce another map. And we're going to call that the archival product, right? So that map will replace the original map because it's actually better. It's got more information in it. Now I'm simplifying it now because we realize that it's not this cut and dry. Really, we have these two products, but we decided that it's just not, it's too far-fetched to do that. So we actually have two stages in between, where we have an operational and a provisional stage. So, this is important for those data users that are going to be using these products, because they will be updated as new data and information comes in, because the availability of data is dynamic. And why limit yourself to day one to have the map when at day 30 you'll have 15 more stations, and at day 180 you could have 30 more stations. So right now this is the way we're organizing it, but you have to draw a line at some point though. So at some point, once we call it archival, it's going to be good to go. So I want to also highlight that this is the February 2022 rainfall map produced on March 1st. And I'm really happy to be showing you this map because it's a long time in the making. And this was actually our first real-time map that we produced. Luckily, a couple of days before the launch, it actually worked, everything executed, and we're so proud to be holding this up for you today. But I want to highlight what it would take to make this map without the effort that's gone into it. The first thing you would need to do is get all the data that I'm talking about. And I can tell you with confidence, there's only 2 people in this entire state that know all of those different places where the data is. And there's really only one person that has a comprehensive knowledge on how to access all that data. So you're really limited on that. Now you can make a map with less data, but I'm talking this particular map with all the data that we had available to us. Then you need to process the data with a quality control, quality assurance, and there's really only a handful of people that do this or have knowledge of this in the state. And then you'd have to interpolate the data. So again, a handful of people that could probably make a good quality rainfall map. Not that people aren't technically able to do that, it's just that that's not in their wheelhouse. They're not doing it. It's just something that's specialized skill, and you have to kind of learn it to make a good map. And then finally, you got to make a map. So you need GIS skills or some kind of mapping tool to make something of this quality, right? So you need, and to say that this could be made on March 1st is a joke. We're talking maybe a year from March 1st, March 1st, maybe 2023, before you were able to do all of these things that I said right here to make a map. And now you can make it in a matter of moments. And for example, I sat my 7-year-old, my 8-year-old son down in front of the HCDP the other day, and I had them both make a map. I gave them about a 2-minute tutorial, and they both made maps in about 30 seconds. So that's really where we've come to, taking something that normally would have taken a year, required a specialized team of people and skills, and reduced it down to a 2-minute exercise that a 7-year-old can complete. And that's really, I think, important to hold that up. Where are we headed with the HCDP? Well, I'm going to reiterate that this is the start. Okay, we're launching today, but as you can see, with all the products coming online, all the opportunities on the horizon, we have much further to go and many more things to do. We're currently working on these near real-time decision support tools with the Hawaii Emergency Management Agency for the fire risk. There's a proposal for flood risk, doing some stuff with NOAA and NIDIS for the drought risk. And then Lucas Fortini's working on an avian malaria model. And everyone's accessing these near real-time data products to do these things. So the data, even though we're launching today, folks are already got their heads around what they can do and how they're going to utilize this data. We're going to continue to build the portal. So we're going to, continue to put in those research highlights in, publications, the products that I mentioned. It's just going to get bigger and more data rich. And every single day, 3 new temperature maps get added. And every month, a new rainfall map gets added. And when the rainfall goes to daily, you just think it's going to be the same number, another 12,000 maps right off the bat. And then I'm also working with the Pacific Islands Development Program, which I work at the East-West Center with Mary Hattori there, and we're working, brainstorming some ideas on how we can start bringing in some Pacific data and create some resources for folks in the Pacific, even through the Hawai'i Climate Data Portal. And then I think this is kind of the low hanging fruit, but also the biggest opportunity is really developing curriculum around this, right? So if my 7-year-old son can make a rainfall map, why shouldn't other kids around the state be able to make a rainfall map or go on the future projection map and figure out what how hot it's going to be at their elementary school in 2100? And I mean, I'm just throwing this stuff out there. We're having some early conversations, but I mean, that's on the lowest level in terms of just functionality, but really there's educational tools that can be developed all the way up to college and kind of downloading out of the box coding syntax and processing data and just utilizing this tool in so many different ways. So again, for those on the call that are interested in this, we can have conversations to talk about where this can go. How can you get involved? Well, we do a social media account each week. We do a one post related to climate in Hawaii or ecology or restoration or conservation or cultural knowledge. And we put that information out there, just one post a week, just to kind of raise awareness and let people know when new things get published or when different things happen. So you can tune in with us on that. You can go on and make a rainfall map. You could take your 7-year-old son and make a rainfall map if you want, just for fun, or you could put it in your proposal or on your presentation, or you can zoom in on this map and figure out what it looked like in your backyard last month. And then you can also contribute. So I mentioned a bunch of these ways. You can tell us how to improve the HCDP. We have a Google form I'll be dropping in the chat here at the break. You can give us some feedback. You can share your ideas for research or research highlight, or you can give us something to post on social media. And then you could also send us your publications so we can put them in the library. So the bigger picture is the world is getting warmer. Yeah, I don't need to explain that to anybody. Look at this graph up here that NOAA put out last year. It's getting hotter, and there's no denying that. And really, the action isn't being taken on a global scale to reduce those temperatures. A lot of talk, but really, it's not. The temperature's not coming down. So it's going to have profound impacts on the natural resources in Hawaii. It's inevitable. Even at the rate we're going, even no matter what we do, there's going to be impacts. So land and resource managers need to find a way to adapt. So at the end of the day, it's great that we have this. It's great that researchers will do analyses, determine how things have changed over time. But fundamentally, data is really important for land managers so that they can get it, they can translate it and interpret it in ways that help them make land management decisions, to help them adapt to climate change, the coming and inevitable changes that are headed our way. Just want to wrap up by thanking the team again. I mean, Tom mentioned everybody. Just want to throw a shout out to Amy Schreiber, who's an undergraduate. That's basically everything you see on the portal has come from her hands in terms of putting up all that information. And she was the only person to apply for this job. And I'm so thankful that we had her. So I got to give her an extra shout out. And then to the data science team, they don't get enough recognition, but they're super talented. And we couldn't have made this happen. So I said for 10 years, we've been talking about it. The reason we've never done it is that the skill set involved in getting this stuff all together is completely out of our wheelhouse. And we really required that data science, climate science combination tag team duo to make it happen. So again, thank you for your attention. Thank you for being here today. And I'm going to pass it to Jared so he can show you the hard work that's been put into the data portal, and you guys can learn how to make a map on your own. Mahalo.
I'm Jared McLean. I'm going to go over some of the features of the portal. Can everyone see my screen? Okay, can you hear me?
Can't hear you very well, Jared. Can you put the mic a little closer? Yeah, thank you.
Okay, so the portal has two primary portions to it, visualize data and export data components. I'm going to go over the visualization first. So it starts with the monthly rainfall maps. This is the monthly rainfall map for last month, February 2022. It will load in both the map as an overlay as well as data stations. So you can view station data for all the available stations. Down here, it shows some of the metadata for the stations and basic information on them. You can also generate time series data for each of the stations. So this is showing all of monthly data for the station that was selected and also daily data for it. The time series, you can go to the specific year. It's for this year, it's not going to be much because it's can zoom in on particular points. To generate maps for different time periods, you can go back a year, we'll load in data for that. So this would be for February 2021, can walk to the next month. Yeah, so this has data from 1990 up to February 2022. There are also legacy rainfall, which is the old rainfall maps from 1920 to December 2012. So we switch to that data, you can see rainfall maps for that. This doesn't actually have station data associated with it, so there's nothing for that. But then there's temperature maps, the monthly temperature maps. So this currently goes through 2018. That if we go to a different station, you time series temperature data for that station. Take a few seconds to load in. So this will basically put in all the station data for that station over the entire range that was active. We also have daily station data, which is updated in near real time. So our latest map is actually from yesterday. So we have a for March 2nd. This is the maximum temperature map for yesterday. This can view station data for that. And then there's also minimum temperature maps, again, updated in near real time. So this would be minimum temperature for state and mean temperature as well. Mean temperature doesn't have station data associated with it, but it does have data maps. So there's several different color schemes that you can choose. Default is Veridis, but you can change to different color schemes to view the data in different ways. You can also upload a custom color scheme if you want, using an XML file. So this is a blue-gray color scale. This is Garcia to rainfall. We do have daily rainfall values, although that is only station data at this point. We don't have maps associated with it. So if you want to view daily rainfall data, you can go with that and it will load in the actual station data. So you can view station data that's available, and soon we'll also have the maps associated with them. And also time series data for that. So, and that goes through January currently. So if I switch to monthly rainfall, I set the map in a way that I would want to generate an image of. Let's switch back to, so we have a USGS style color scheme, and so for the map, you can generate an image of the map. You'll download that as a PNG file. And you can see this is export from the portal. So you can do that with it's whatever is in the map window. So you can adjust the size of the map window so that it's full screen. or you could take, if you just wanted for the Big Island, adjust it so that it's just focused on that. And it will basically take an image of whoever is in this box. Additionally, we have several different base maps that you can use. So if you don't want the satellite imagery, you can change that. You can also toggle the data maps and data stations on and off based on what you're interested in. Yep, and you can change the date as well. You don't have to use the walkthrough thing. So if you have a specific date that you're interested in, let's say I want to view for March of 1998, you could go to that and it'll look at data. So those are the main visualization features. For the actual data export, which is the second part of it, you can.
Jared, can you show the download, Jared, on how to actually download the JPEG?
For the map itself, it's this button in the corner. So where it says export map, right under the zoom buttons. So if you click that, it will generate an image and download it from the browser. So now if you want to export the data from the application, you can choose the data set that you're interested in. So if I wanted monthly rainfall data, and then let's say from 2018 until 2022, this shows what files are available for this data set. So there's rainfall map, standard error maps, anomaly maps, anomaly standard error maps, metadata, which is required if you download any of these, and then station data for that time period. So if I select a couple, you'll see that this is automatically selected. There's different spatial extents for all the files. So the default is statewide, although I can also download files for individual counties if I wanted. Once you select that, like that files, if the package is too large, it will force you to download as, it'll force you to have an email package sent to you instead of downloading it in the application itself. If the package is small enough, you can download directly from the application. But if I put in my email and hit export items, it'll generate a request, and in the coming couple minutes, I'll receive an email with the download package. And if I reduce the amount of data that I'm requesting a little bit, you can also generate it directly in the application itself if there's big enough files, and that will immediately download the package. And then, yeah, this has all the data that was requested. So different spatial extents, standard error maps for the different dates. And then if I go to my email, this should have the download package that was sent to my email. So, and these are stored on the server for 3 days. So you have 3 days to download the package before it gets deleted. And we can add multiple different types of data. So if I also wanted temperature data, you can set that, add the files for that, and it will download anything that you add to this section. And yeah, that basically covers the main features of the application. So now I'll pass it off to Dr. Keri Kamelamela from the Akaka Foundation, and she'll present some of the cultural resources behind the project.
Sorry, Katie, you're muted.
I had to be the one to do that. It was me. Aloha, I'm Keri Kamelamela. got a couple chuckles. I'm calling in from Hawai'i Island. I don't know how to shut off my closed captioning, so that's a benefit if you guys can see that. Thanks to Ryan for inviting me to help share about the Cultural Resources tab, help put together by the Hawai'i Climate Data Portal. They came and talked story with us a few times, and so we're still developing and hoping to get more input. So to do some of this cultural resources research, we got support from members of WRRC, PICAS, Forest Service, Akaka Foundation for Tropical Forests, Mānoa, and Hilo. And so what are we talking about? Tom shared in the beginning the Hawaiian perspective within Hawaii and that relationship. And that's really the goal that Ryan really shared with us, was his experience working with communities and his want to intersect more in his climate research with supporting Indigenous points of view. And so Ahupua'a system is one of those examples within Hawaii of where climate knowledge is being adapted, not just in one area, but in many micro ecosystems and environments and climates. So this is a model that I've been developing about knowledge of Indigenous peoples' approach to understanding climate change to make it maybe a little bit more tangible. So the center is always the land, and we as the people are the intercept and the observers between the environment and the elemental phenomena. And over time, in a certain place or in an area, we develop specific knowledge, and then we pass on that knowledge over time when we develop to see patterns. And that's what Tom's talking about within traditional languages, Hawaiian in Hawaii and in other places. So these are items that we tried to, again, it's a portal. So we didn't want to replicate resources or anything like that, but provide a sample of what is available and resources that honestly I use, and cultural researchers who intersect with climate perspectives in drought, El Nino, hurricanes, king tides, also reflect on these materials. So in the cultural resources tab, there's a climate glossary, educational resources. I'll share a couple of those: archival newspaper access, overview of Hawaiian lunar calendar, and a couple examples of Indigenous local knowledge projects intersecting with climate change. Within my project is drought, and then some other dryland agricultural projects that highlight Indigenous knowledge application to research to improve agriculture. So Ryan, I saw it was so nice when I was making this slide that cultural resources in the center. I thought that was really cute. And that's fun because it was easy to find. So it's right in the middle when you get there. When you go into it, again, these are the different sections. I'm just going to go through a couple of them to show you an example and some of the things that I think would be useful for students and researchers. So sometimes we think of Indigenous knowledge as not living. And so these are some courses that the Hawai'i Climate Data Portal crew put together from the University of Hawaii. And we also have some from the University at Hilo. So I'll be able to share those over with Ryan later on. But if you're interested in things and diving deeper in Indigenous methodologies, you can go and contact, and whether you're a student or a researcher, and get more insights or books that you want to read. Also in the educational resources under the web is common sites or well-used sites such as Papakilo, which is organized by the Office of Hawaiian Affairs, and Ulukau, which I believe is the University of Hawaii at Hilo, as well as organizations that integrate biocultural knowledge in their research today. So this is just a look at Papakilo if you've never seen it. You can look at historical maps. You can look at different terms that you might find, place names. And so the future, I think, that we're working with in our little climate indigenous hui is uplifting place-based vision, community-based missions, and subsistence-informed driven science so that it becomes important and relevant to the people who are engaging and also developing relationship with researchers in these areas. And something that'll be important is like a program Dr. Alagado has been conducting with the Kulananoi'i program to help researchers gain experience if they want to work with communities directly, besides just looking at historical resources. So I'm going to hand it back to you, Ryan. Thank you so much.
Thanks, Katie. That was awesome. A veteran move in putting together an agenda on a meeting like this is to put the break in, knowing fully that you guys we're going to go over at some point in time. So that's kind of where we're at right now. Just a little bit over our time. So I did want to actually we're kind of right on time. So two things right now. I'd like Michelle to put the Google form into the chat. And then everybody that's on the call, we'd like you to take a moment to click open that Google form and fill it out if you can, or you can go off to the use the restroom or anything. We're going to come back in just a few minutes, but we're also going to take a few questions. And so if you want to turn your mics on or you turn your cameras on now, you can do that. And I'm going to go through some of the questions that are in the chat that have been put in the chat right now, and answer them and call on some of the other presenters to do that as well. So can you put the gallery view on, Michelle, also? So we had a question, will there be APIs that access this data, and similar to the Rainfall Atlas? And excuse me, the answer to that question is yes, we do have APIs that are available, and we can get those to you, but a lot of the folks that are using the real-time environment are just accessing that stuff off the API. So yeah, just reach out and we can get you that information on how to access the data via API.
Would you let Sean comment on that?
Yeah, Sean, that'd be great. How would folks, what was the best way for them to access that information?
There's also a question about it was phrased in terms of REST endpoints. So you might hit that one at the same time.
Yeah, so the question is there REST endpoints? Yes, there is. And actually, I'll talk about that in the presentation a little bit later. And yeah, my email will be posted at the end, so we can, or you can email somebody else and we can discuss like how you can get access to some of the APIs and endpoints that we have for this. And yeah, we built it with that in mind, so.
Okay, next question. Has there been ongoing efforts to provide estimates of daily heat and humidity measurements combined to generate heat stress index? Well, that's kind of a low-hanging fruit. Once we get the relative humidity and the temperature maps, we can do that on a daily time step. But I think the heat stress index is typically counted on an hourly index, but it could be done at daily also. But one thing we didn't mention is that eventually when this Mesonet data starts coming into the portal, we will be moving to the hourly time step. So right now it's daily and we're getting started. But as time moves on and more data comes in and we have a plethora of hourly data, then that data will be available, and things like near real-time heat index, and even in terms of decision support and emergency management, those products will be available. So it's coming. If you're looking for hourly data now, there are some resources we can direct you to. We are archiving it. We're just not pushing it forward into the portal just yet. We're just focusing on daily for now. Will the portal maps display percent or normal monthly precipitation or monthly precipitation percentiles? I think that, that'd be a great thing to put in that Google form. I think that's a great idea. It's nothing we're doing right now, but I think it's something that's a low-hanging fruit that we could do. Tom, you have any thoughts on that?
I think we already have the anomaly maps as an available for download. I don't think they're available for display in the visualization tool. But those anomaly maps are basically just departures from normal.
Yeah, those are available for download. And the question, can we download a customized map? Yeah, you can zoom in to whatever extent that map, that resolution will allow you to go and download it, and it will get the same features. The scale will change according to the map. The color ramp will be there, and yeah, you can zoom in or zoom out. You can change there's a slider on the window there to make the map to whatever extent you want. You can minimize your browser and just get the map perfectly the way you want it looking for the island, and hit the download button. Another thing you can do is you can download those time series. The time series show the monthly, annual, and full station record. So the little gridded time series of daily data, there's a feature up there where you can download that as well, and put those into your presentation or your report, or even your publication if you want to. So again, that could be customized for an individual station. And then the last question I see here is how can we download past hourly rainfall data at a specific station? Again, that's something that we are archiving, but we just don't, we're not pushing that forward. So I'd say reach out to us, and we could see you know, what we can get for you. Usually access Hawaii rainfall data 90-day archive and try to correlate flooding with daily rainfall occurrence. Will daily rainfall also be introduced into HCDP? Well, yeah, so the daily rainfall is available now. We do have those, that daily time series updating every single day, and that will be updated as new data comes in. But the daily maps themselves, again, we have a methodology, we just haven't got to executing it yet. So they could be as ready as early as the spring, summer, probably fall at the latest. At the rate things change and happen and obstacles arise, it could be even later, but we're optimistic. We're continually optimistic in the situation.
But just to emphasize, the daily station rainfall data are already available and are posted on those maps in the visualization tool.
Okay, so I think that's it for the questions. I think Maddie, you're next on the agenda. If you want to get your presentation queued up, we can get you going here.
Okay, can you guys hear me all right? Okay, well, I want to get this out of there. All right. There we go. Hello, my name is Matthew Lucas, and I am a climate data analyst at the Water Resource Research Center under Tom Giambelluca. I've been working with Tom and Ryan on this project. It actually didn't start out. I don't think you guys remember, but we never really were like, we're going to make a portal. We were more just like, we're going to make a way to make automated maps. And then the portal became such an important part. So yeah, so I'm going to be talking today about the automated rainfall mapping process. And I am just going to go through everything. So thank you to all our funders, and here we go. So brief overview, I'm just going to walk through how we make a map, and Ryan kind of did this, but I'm going to go into a little bit more detail and kind of just show you what some of the data looks like, and maybe some visualization so you can kind of understand what's happening. And then we're going to go into some of the, I'll go through all those steps, and then I'll go into some of the products. Hopefully we'll have time to go through some of the products, and then small chance, but maybe we can do a little teaser on the daily rainfall. So that being said, the first step in the process is data acquisition, and our two main data sources are HADS, and the National Weather Service puts out an hourly report that's called the RR5, and we scrape the one on the right, and we download the one on the left. And we basically do this whole thing. Our stack for me is we're doing all this in a Linux environment with a cron scheduler, using R, and they're containerized in Docker. That's just for the geeks to understand. But the main thing to take away from that is that everything is open source. All this programs we've developed has been open source. So when we do that, we get all this sub-daily information and we boil it down to a day, and we do this on the day. And so we end up with a table like this, where we have our stations, our metadata, our vetted metadata, and then the daily station values for each day. But if you'll notice, there's a couple of values. This is millimeters per day. There's a couple of values that are quite outlandish. And this is just straight, this is literally a piece of data I pulled off of the portal last night. And so you can see there's just some amazingly huge values. But also what is harder to see is that there's some values here that are also don't really match the pattern of rainfall. And so when we do our QA/QC, our automated QA/QC, which is a machine learning algorithm, we use a random forest machine learning algorithm right now, we transform those to no data values. So now we have no data values in there. So an erroneous value won't throw off the estimate of our map, but we're missing data now. And so what we do to fill in the missing data is we gap fill it. And I don't know if you noticed, some of those big values in the top didn't get gap filled, and that's because we do have gap filling criteria. There has to be a station that has a close relationship to it. There has to be a certain amount of data from the target station in order to make this relationship. So those ones actually didn't get gap filled, but just removing those values is huge. That helps out our effort a lot. And then we filled those values that were also flagged, as well as other values that were just missing because the station was down. And we have this optimized method of doing this that Ryan published a paper on in 2020. This is the paper right here, characterizing uncertainty and assessing the value of gap-filled daily rainfall in Hawaii. So we have graphs to show that we're doing it in the most optimized way. And then we take that daily after we've gap filled it and we make it into a monthly aggregation. So this is kind of what it looks like going to monthly. So here's January and here's February station data, where we boiled it down again to one number. Okay, so just to go back a little bit to talk about the QA/QC. So how our QA/QC works is essentially we're leveraging a relationship that is there, but it's not a rock solid relationship, but we leverage enough data that we are actually looking at the 10 closest stations to our target station and their value, their rainfall value. Here we've converted it to a percentile of occurrence to the target station. So as you can see, like this is cycling through first closest through the 10th closest, that relationship kind of starts to get spread out. The data, the brighter colored data, the yellow and the green is more points, and the darker colored data is less points because it's so many points in this. This is like 30 years worth of data. So you can see that relationship kind of starts to spread apart as that 10th closest station, but there's a pretty strong relationship there in the first closest station. And what we do to put this in a spatial context, this is, you can see the legend there is the percentile, or the probability of a rainfall occurrence. So again, we've transformed rainfall occurrence into probability. And you can see the triangle is the target station, and the color is the probability, and the dots are the 10 closest stations. So as these are cycling through the first closest to the 10th closest, you can see that sometimes the colors match closer to the triangle, and sometimes they don't. And this is a simulation where I threw in bad data here and I had real data, and so you can kind of see what it looks like when it doesn't match and when it does match. But this is kind of the idea that's happening behind the background. And the whole reason that we're able to do this is because we made another series of maps using Ryan's original daily maps, where we actually calculated the probability of any amount of rainfall. We calculated the distributions of every day, or all the days across space. So basically we have these maps where we can say, what's the probability of a quarter of an inch of rainfall or greater for any given day? And so that allows us to normalize rainfall across space because we do have such tight gradients. So that's how we get to 0 to 1, the conversion of 0 to 1. So once we have that data, we take a mean map. So we've done our QA/QC. We're back to our monthly station values. So we have our mean map of mean monthly rainfall, and we have our stations and our station data, and we actually calculate the difference between the observed and the predicted, and that number is then transformed for mathematical reasons for us to make a better fit with the kriging into that is transformed into an anomaly, and that anomaly is then used to produce a variogram. And if you don't know what a variogram is, basically a variogram is trying to make a model that is the distance from any given location to the value of close to far away stations. So it's a way to fit that together. So distance is on the x-axis, the variance, the semi-variance is on the y-axis. And so how this actually looks is what we end up getting on the output of that is we can then use that variogram to apply it across all space and between all stations and everything like that. And then we make an anomaly map. So now we have a map of the anomaly of rainfall. So how different is it across space? The reason we do the climate aided component is because sometimes we don't have stations at the upper ends of our rainfall gradients just because stations have gone out. But we do know that there was high rainfall there at some enough to generate a high mean value. So we have our anomaly map and we have our climate template. And then to convert our anomaly map into a climate template, we simply multiply it by it, and then we get our final rainfall map. So this would be a final rainfall map. So just to go back to a variogram, even if you have a perfect looking variogram, which this is an idealized looking variogram where you have a correlation and uncorrelated, you can see that basically as the asymptote reaches 0 on the curve, you get an uncorrelated relationship. Even if we have a perfect variogram, we can still produce a pretty bad looking map. And so this is typical of an automated kriging. Not all outputs, but a lot of outputs come out this way. And so what we actually did is we krigged a bunch of maps with a bunch of different data sets, combinations of rainfall data sets. I think we did like 30 years times 4 times. So it was 120 years worth of rainfall maps. And we manually classified them. So we made a bunch of maps. And we manually classified them as good, bad, and ugly, which we don't actually use as terminologies anymore, but I did use these terminologies when we classified it. And we threw out the ugly, and we threw out the bad, and we took the mean nugget and range values from that variogram and made the mean nugget and range values for the good maps for each island, each county, which is the extent that we're making our maps. Then that allowed us, so we have our nugget values and our range values where we can fix those, and then the model is allowed to vary other components of it. And we re-krigged a map that would look like this. This is an automatic output to make it look like this. And in doing that, we basically had 4 different ways that we krigged. So we krigged where we let it go automatically. We fixed the nugget, we fixed the range, and we then fix the nugget and the range, but the fill was still allowed to vary. And so we did this, and we actually did it 3 times because we have low, medium, and high. So like say you had a map and it produced a bad map, the first scheme didn't produce a good map, we would go to the medium values, remake the 3 maps, check those, still produced a bad map, and then go forward with the last one, let's say it was true, and then we would get our final map. And I like to say too, the way that we actually classified this % realistic or % ugly, as it was the working term, was we had another random forest classifier that was trained in order to do so. So just an overview to show you of everything like that we did. And there's more detail in this paper that was just published that I'm the lead author on, optimizing automated kriging to improve spatial interpolation of monthly rainfall over complex terrain. And so how did we do? Well, this is results from the paper. This is 30 years of data from 1990 to 2019. And overall, we did pretty good. The right-hand side is the leave one out cross validation of every monthly station for the whole 30 years across all counties. And the left-hand side is a histogram of the maps, where the maps are actually units. You could see that our average, which is the red dash, and our standard deviations of each map and what our squared value we actually got from a leave one out cross validation. And you can see this is our per county values. So this is all in the paper, but just wanted to show you that overall we did pretty well. So just real quick, I don't think we have that much time, but I'm going to go through really quick the products that are in the HCDP. So Jared mentioned the download page. So when you go to the downloads, if you go to rainfall under data set and you go to monthly under time period, you can see that you can collect click a rainfall map. And this is what a rainfall map would look like if you were to plot it. It's a GeoTIFF that is around 250 meter resolution, and it is WGS lat long projected CRS. And we provide that grid, which is also on the viewer, but we also provide other grids. So this is the anomaly map. So this is an anomaly map for this same map here. And we also provide a standard error of not only the anomaly, but also the rainfall itself. So the standard error unit would be anomaly. And then the standard error of the anomaly would be, the unit would be anomaly, and the standard error of rainfall, it would be millimeters. So when you click any of those maps though, you do get that bottom one, as you can see, automatically comes on. So you're getting these metadata and error metrics. And so what that actually looks like, this is a text document. It's text tab delimited, so it's human readable, but it's also machine ingestible. And essentially, this is just a document that goes through a bunch of stuff you might want to know about the data set. So there's a bunch of information in here, including a layman's statement that you could just read and understand how well or what we did, and then how well did this actual data set perform, as well as the actual error metrics on the bottom there. And then there's also station data. So when you're on monthly, if you click station data, this is what it's going to look like. I showed you this before. Essentially, it's going to have our station metadata. There is lat long when you download it. I just didn't show it here because it wouldn't fit on the slide. But you can download the station data, and it's going to come out in yearly files, and then the columns are going to be monthly. And if you go, and this is the monthly values, and if you go to rainfall daily right now, you have two choices. You have station data unfilled, and you have station data partially filled. So the unfilled data, that's that data that I first showed you. So this is the rainfall data, and just be cautious because it does have all of the errors in it. And the reason we wanted to provide you with this is if you want to start working on your own QA/QC, or you have your own things you're interested in, we're not gonna make you look at our, or just only be able to get the QA/QC data from us. So this is the raw formatted data, but like be cautious of that. You have to do QA/QC on this data in order to use it correctly. And then the other data that's available is the partially gap filled. So that has been QA/QC'd, and it also has had some values gap filled. All right, do I have time for a daily teaser, Ryan? I can see you. No?
Yeah, I mean, just go ahead.
Okay, so just a real quick teaser, future daily rainfall. We're trying to take an approach where we actually are grouping daily rainfall maps into patterns, and then using that like as a rainfall pattern per county. And so this is what some patterns, one pattern analysis generated for the Big Island. I think we got 18 patterns here. And take a look at one pattern right here. And so basically the idea is that without using a pattern and using just a climate aided interpolation and an estimated daily mean, we produce a map that in our square root of 0.31. But when we use this pattern as to generate the anomaly map, we produced a way higher error metric, way higher R squared. So that's a little teaser of what's coming. And yeah, I'm done. I'd like to thank everybody. And if you have any questions directly to me, feel free to email me or try to get them answered here. So that's all I have. And up next is Dr. Keri Kodama, who is a postdoctoral fellow with WRC. So thank you.
All right, thanks, Matt. My screen up. Right, can everyone see?
Yes.
Okay, great. So yeah, I'll be talking about the daily temperature mapping effort. And as Matt said, I'm a postdoc who recently joined the WRC team last year, and I've been developing the temperature maps with the help of many co-authors and collaborators who helped me with data access and working out the methodology. So first I want to give a bit of a background on the data set we have available. So on the HCDP right now, we have a 32-year gridded temperature map data set, and it's continuous from January 1990 up to the present, and it's updating in real time. And we have maximum, minimum, and mean temperature maps over a statewide range, and also available for the 4 counties. And it's a high resolution uniform grid of 250 meters. And because it's continuous and in near real time, it has many applications for things like wildfire risk prediction, energy consumption, climate modeling, and environmental research, and many more. So there are a number of difficulties in creating temperature maps in Hawaii. A lot of factors that made it challenged to get a continuous uniform series. And so one of them is the existence of the well-known trade wind inversion. And this is when the moist oceanic air rises up the mountain, meets subsiding dry air from larger scale circulation. And if you notice on like high mountain ranges like Haleakala, Mauna Kea, Mauna Loa, you see a pretty flat cloud layer at a certain level and completely cloudless skies above it. And that's where the inversion occurs and creates pretty sharp change in atmospheric conditions where those 2 air masses meet. And that sharp change, anytime you have a sharp discontinuity, that just makes creating uniform maps of any climate variable pretty difficult, as getting a smooth interpolation across that discontinuity is mathematically challenging. And in general, because of the sharp changes in terrain in Hawaii, we just have a large diversity of climate. At sea level, we can experience pretty warm temperatures, while on the exact same day, there can be locations that are dramatically cooler at high elevation. And these terrain differences affect many features like rainfall, humidity, wind speed, et cetera. And all of these things are major factors in affecting the local conditions, including temperature. And then on top of all of that, so we have rapidly changing conditions in space. And on top of that, we have a lot fewer coverage of temperature observations. So in comparison to rainfall data, the figure on the left of the station maps comparing rainfall and temperature availability it's a bit older, but it still illustrates the substantial difference in terms of the stations that are reporting rainfall in comparison to temperature. And so that makes spatial interpolation techniques like the ones that Maddie covered earlier a lot more difficult to apply to temperature where data is more scarce. So it becomes useful to just use environmental variables that are influencing temperature to create a model of it. And so there are numerous factors that can influence temperature, such as location in space, elevation, humidity, wind. And co-authors Aurora Kagawa-Viviani, Tom Giambelluca did a lot of work evaluating the different factors that influence temperature. And the picture on the right shows a lot of the work that was done in just taking all the different potential models and variables that could be influencing temperature and just seeing which models ended up being the most effective. And what we found was that elevation is the dominant influence on temperature, and that adding the additional variables doesn't significantly improve the effectiveness of the model in terms of compared to the computational cost of having a more complicated model. So this is good news because this means we can estimate temperature with a pretty simple linear model of using estimating temperature as a function of elevation. So we have 216 measurement stations that were active over the 32-year record at some point. And so the first step in creating a temperature model is to gather whatever observations we have available for the day that we want to create a temperature map. And so once we compile all of those data, the next step is to create a linear model. So plot the data in with respect to elevation and generate a best fit line. And one of the important factors in the methodology is that we account for the trade wind inversion, the discontinuity that occurs in trade wind inversion, by splitting the linear model above and below the mean height of the inversion. So we essentially have a different model for lower elevation data versus high elevation data. And we find that this is more effective. It produces more accurate temperature estimates than trying to just force one line to fit all of the data points. And so now that we have the best fit line, that's our linear model, and we can use that to estimate the temperature at any of our desired grid points, wherever we know elevation. And that's pretty easy measurement to get. So we're able to create maps for each county across the state. And as mentioned, there are a number of other factors, specifically the reduced coverage of temperature observations. And in a real-time environment, we have to be able to handle issues like missing data automatically. So looking at this example from a particular day in Kauai, there aren't very many data points, and we're also missing some key points at higher elevations. And even on islands where we don't have a mountain that's above the trade wind inversion, it's important to have some of the higher elevation stations to kind of fix the trajectory of the temperature profile. So as you can see, if there's a lot of points that are clustered in a small range of elevation, it's going to be hard to establish how temperature evolves with elevation without those higher stations. So what we do is we use some gap filling procedures to estimate what the values are at these higher elevation stations using other stations that have data available and are similar in temperature profile to the missing data points. And we use those similar stations to estimate the high elevation stations that are missing. And outside the gap filling of the high elevation, if there's still not enough data, we sampled data from neighboring islands as well to produce a sufficient sample to generate a more effective model. And we find that the differences, any errors that are incurred from using outer island data just aren't as significant compared to the improvements that we get for the model that we generate from having enough data to produce an accurate model. So it's better to use outer island data rather than not have enough data to generate a map. And then lastly, there are cases that if the stations are reporting just unrealistic data that don't match the general temperature profile, these are filtered out and discarded before doing the best fit analysis, and so that they don't skew the evolution of the temperature. And so going through all of those, overcoming all of those obstacles, we are able to produce our statewide temperature grids for max, mean, and minimum temperature. And again, I want to reiterate that these are continuously updating to the present day, and it's a seamless data set. And because of the linear model that we use, we have a reduced dependence on the proximity of stations to the location that we're trying to estimate. And so that allows us to reduce errors from the previous temperature data set that we had, in addition to extending the record in time that we have available. And just a quick overview of the actual products that we have available on the HCDP are the temperature maps on their daily geotiffs for all of the 3 temperature variables, and the corresponding uncertainty maps of the standard error. And then the daily station observations, and these are the raw observations, so they haven't they don't come with the quality control that's been done or the gap filling. So it's just the original data that were used to go through the entire process. And then lastly, the data description and metadata files that give the estimates of error and goodness of fit. So that's all I have, and I'd like to turn it over to Dr. Abby Fraser, who is an assistant professor at Clark University, and she'll be talking about downscaling products.
Thanks so much, Keri. All right. And thank you everyone for sticking around. And I just am so excited to be here. I've been working with Tom mapping rainfall across Hawaii since 2009. And this just is a really exciting day to launch this this data portal. So the product that I'm actually, the products I'm talking to you about in the next couple of minutes are actually not available on the data portal yet, but we hope in the coming months that we will be able to make these available to you. So, you know, everything we've been showing you so far is looking at historical climate conditions for the state of Hawaii. But as many people want to know in their work, they want to look at how climate will change in the future. And to do this, we use global climate models to simulate Earth's future climate under different greenhouse gas scenarios. However, as you've gathered by looking at these complex spatial patterns we have, especially in rainfall, Hawaii has extreme gradients in topography and therefore climate. And these global scale models that are used to look at future climate projections can't capture these small scale processes on the topography. And in some of the models, the entire state may fit in 3 or 4 grid cells. So you can see in the image on the right, you know, a typical global model resolution does not resolve all of the complex patterns that we see in especially rainfall across Hawaii. And so we need high resolution data to capture the steep gradients and complex local patterns. So as those of you familiar with the Rainfall Atlas know, you can have a change in rainfall over 6 miles, going from 15 inches down at the coast to over 360 inches in the mountains. So really extreme gradients over short distances. So the technique that's used to relate the global model results down to the local scale is downscaling. And there are 2 main types of downscaling, statistical methods and dynamical methods. And I won't go into the details of those. What's most important here is that there have been several projects that have taken the global models and downscaled those future climate projections for the state of Hawaii. And we currently have several of these projections available. However, they're fairly difficult to access and use. And so one of the projects that we're working on right now is to really standardize and create these data sets that make it easier for folks to access the downscaled data. So one of the ways we would like to do this is to add these available projections to the HCDP. So I will just briefly go through some of the results from, these are results from 2 of the different projections. So a statistical result on the left, Ellis and Tim, 2017, and a dynamical result on the right for annual temperature change by the year 2100. And this is for a high emissions scenario. If you're familiar with the modeling terms, it's the RCP 8.5. So under this scenario for both of these models, you see that there's pretty strong agreement that the future temperature across Hawaii indicates robust warming, with the strongest warming shown at high elevations. So you can see the darker red colors at the over the peaks of Mauna Kea, Mauna Loa, and Haleakala. But we do have differences as you look across these 2 different models. So this is a look at annual temperature change. When we look at rainfall, the story gets a little bit more complicated. Again, we're showing results from 2 different projections, so 2 different modeling techniques. And unfortunately, you see pretty different patterns of future rainfall change. The statistical product is indicating an overall drier future. I think the average for annual rainfall change by 2100 under this high scenario is about 28% drier, while the dynamical model indicates pretty pretty close to 0% change overall, about 2% drier. You can see there's pretty strong differences across space. And one of the ways we've been working on trying to help visualize this to make it easier to understand is we've tried basically creating a mask over the areas that disagree in the sign of change. So for these two products, the maps are now just showing you the areas that agree, at least in the sign of change. So will it get wetter or will it get drier in the future, according to these two projections. So from this, we can start to sort of see some general patterns, although the magnitudes are quite different. But in general, these models are both in agreement that leeward areas generally can expect to see drier conditions in the future, and same with the high elevation areas. So high elevations are getting warmer and drier. And then the windward areas may be getting slightly wetter for Maui and Hawaii Island. And then we can do the reverse and look at areas that disagree in the sign of change. Definitely some areas where the models just have a high level of disagreement for future rainfall change. So what will be added to the HCDP? We're planning to add these downscaled future temperature and rainfall layers at the same 250 meter resolution. They will have future change, like the maps I just showed you, as well as future means for the RCP 4.5 and then the higher emissions RCP 8.5 future scenario. And for some of the models, we have mid-century results. Most of them are end of century. And again, we'll have some statistical and dynamical downscaled results. So we're hoping to make these interactive layers on the Hawai'i Climate Data Portal. So in that dropdown, you will be able to choose future rainfall and future temperature and click and see what the projected changes are where you live. And while I'm here, I will give a very quick plug for some additional products that are coming down the line. I know there's a lot of new work on this frontier, but one of the things we're looking to do is take the existing products and calculate some extreme precipitation metrics. So looking at future projections of drought and heavy precip. So we're definitely open to stakeholder input on what kinds of metrics people want to see. And you'll notice this photo in the background is not Hawaii. This is actually Southeast Alaska. So this is a project funded by the Alaska CASC and Pacific Islands CASC, or Climate Adaptation Science Center. So we are working with the folks in Southeast Alaska who also experience these same steep climate gradients to work on translating and getting these new extreme precipitation projections together. So I want to make sure to thank especially Oliver, Ellis, and Tim, and Shunqi Zhang, who have provided a lot of these downscaled data, and feel free to email me with any questions. So thank you all.
Okay, I guess I'm batting cleanup here on presentations. Okay, my name is Sean Cleveland. I am a cyber infrastructure research scientist in the Information Technology Services Cyber Infrastructure Group for the University of Hawaii system. I'm going to be presenting on some of the technologies that are powering the Hawai'i Climate Data Portal. So two of the main ones we're going to talk about is TAPIS and containers. And there were some questions about APIs and things, so I will be discussing some of that in this as well. And Michael Dodge, he's one of our students. He's also did a lot of work on some of the stuff in this presentation. So I want to thank him, as well as Jared McLean, who gave the fantastic demo earlier of the Climate Data Portal. He's one of our research software engineers in Information Technology Services Cyber Infrastructure. So he's also one of the folks on our team. So the topics that I'm going to cover are, I'm going to do a little background on how the infrastructure came about for the Climate Data Portal, the technology platform that we're leveraging called TAPIS, containerization of some of the workflows, so some of the stuff that Matt has been working on, and then also some of the visualization and download features and sort of how they actually work. So a little background here, let me close this. Can I hide the controls? There we go. So the established program to stimulate competitive research, the Hawaii EPSCoR, has been a program that's been around for the last 21 years. It's a National Science Foundation program. The Hawaii EPSCoR has been successful in getting over $68 million in funding for this, essentially to try and innovate science across the state of Hawaii, build capacity, and then create some workforce paths. And it's been pretty successful doing that. I bring that up because this is what helped fund some of the infrastructure projects that the Climate Data Portal is built on top of. So the current Hawaii EPSCoR Track 1, this $20 million grant, is we're sort of at the end of this, but this is the Ikiwai project, Securing Hawaii's Water Future. This is one of the projects that has put in all sort of the capacity for us to actually build this Climate Data Portal. And both Jared and Michael were actually students. Jared was a graduate student when this kind of project started, and he started working with me on some of the Ikiwai project, and Michael has he's been working with us as an undergrad. So Ike means knowledge, Y means water in Hawaiian, and so that's kind of the idea behind this project. The idea was bringing together data, models, computation, analysis, and visualization all in sort of one platform to enable simpler access to data and tools for our researchers, community members, water managers, so they can make better decisions. And so we built a platform that was sort of a centralized infrastructure, technology infrastructure that served out decision support tools on groundwater recharge that we've helped build with the USGS, this precipitation mapping, which has actually evolved into what the Climate Data Portal is now, some workbenches for our researchers to store and manage their data, run computational jobs, annotate, publish that data, share it out, do different analysis. And all of this stuff was powered by, was paid for with help from EPSCoR and the National Science Foundation. So when we were going to build the Hawaii Climate Data Portal, we asked ourselves, what are the features that this should have? It should have discovery, should serve data and the data products for climate. It should provide interactive tools to explore and visualize this data, generate monthly and daily climate products, and provide additional resources related to climate in the state of Hawaii. So we're like, how do we do that? Let's use a technology ecosystem. And so we built this Climate Data Portal on an ecosystem of open source. Previous work through the Ikiwai project, the TAPIS project I'll talk about, and then national and local resources like the National Science Foundation Jetstream 2 cloud, as well as our local Mānoa HPC system for doing, running some of the models and the data and things like that for the Climate Data Portal. So what is TAPIS? It's a joint project between the Texas Advanced Computing Center and the University of Hawaii. Our group in Cyberinfrastructure, we do a lot of active development on this project. So it's a National Science Foundation funded open source scientific framework to support research. In general, it's a framework to support any domain science. It provides a lot of tools and software hosted and managed by other folks to help accelerate researchers' timeline to their analysis, their discovery, and their publications. More technically, it's a set of APIs. So it provides authentication, authorization services, database persistence, to records provenance on actions taken in the systems by users for doing compute, moving files, all hosted, like we said, like in the cloud and maintained by other folks. So it's fairly popular. In the last year, we had 51,000 researchers leveraging TAPIS across a number of different projects and 15 gateways. And more importantly, the Ikiwai Gateway leverages it, and so does the Hawaii Climate Data Portal. So TAPIS, the services for TAPIS APIs basically fall into kind of 4 areas. One has to do with authentication and security. The other one's metadata management. So storing records that you want to store information about, and we leverage this heavily in the Hawaii Climate Data Portal for storing information that we'll talk about a little bit. Data management and code execution. So we leverage this for the workflows and moving data around and serving out the data. And then streaming data and events and functions. So this one we're going to be leveraging for the Mesonet project that will be upcoming. So how does TAPIS support all of those things that I just talked about? Basically, there's kind of 3 core things that we can discuss: APIs, REST, and JSON. So if you have heard APIs tossed around and you don't know what it stands for, it's application programming interfaces. And this is really just the way that 2 software programs can kind of talk to one another. So it's essentially both pieces of software can present an interface that they've described that they can just, exchange information back and forth. So if a program is written in R and a program is written in Python, if they have an API layer, they can talk to one another. Basically, if you use a laptop, you use a mobile device, you're leveraging APIs at some point. Most of the internet is powered by web APIs, and so TAPIS leverages those as well. REST, you may have seen REST come up in the chat. What is that? It's representational state transfer is what it stands for. It's not actually a standard or a technology, but really an architectural style. It was devised by Roy Fielding for his doctoral dissertation, and it uses most existing web standards. The basic thing you can think about is a RESTful system is divided into a client and a server, and the client makes requests or passes messages to a server, and the server does some kind of something and responds back. So in this example here, a client says, please insert some data into something, some service, and the server says, okay, I did that, and then tells the client that they did it. So that is sort of one of the concepts that we leverage. The last one here is JSON. So this is a JavaScript object notation. So we need some way for our APIs to exchange information in general. And so JSON provides a lightweight data interchange format for doing that. It's also easy for humans to read. So there are other formats, binary and things like that. But if I get a response from a computer with that, I can't read it without having a computer to give it. I can print JSON out and read it. So this is just an example. If you're familiar with Python, this kind of looks like a dictionary. And so just know that we use this for storing information and passing information back and forth. And TAPIS uses it, and so does the Hawai'i Climate Data Portal. All right, so how do researchers make use of TAPIS? Since it's REST, you can do curl calls. A lot of folks are familiar with curl. There's command line tools for being able to interact with TAPIS. There's a number of software libraries. There's one for Python. There's a number of web applications that are built on it. Like I said, 51,000 researchers used it last year. We have a couple gateways that leverage it. EKY and Hawai'i Climate Data Portal I already mentioned. These tools will allow researchers, third-party developers to actually leverage the Climate Data Portal tools and data that are inside of there. So we wanted to build this to be extensible. And just to follow up, the Mesonet will leverage some of these tools for sharing data with Mattis, so publishing data out to some larger repositories. Okay, so now I've covered TAPIS. I'm going to cover something about the workflows and containers. And so thanks to Michael Dodge for doing a lot of work on containerizing our workflows and getting those running. So what is a container? If you're not familiar, the whole idea here is to combine all the dependencies that your software or your workflow needs. So the operating system, so the version of that, any libraries that you would have installed in there, the code that you actually want to run, any data dependencies that you would need, all sort of in sort of a, you can think about this box container, so this artifact that has all of those things. And then you can run it in a container environment. So Docker, Singularity, Podman, Kubernetes, those are popular runtime environments for containers. Why would you use a container? Well, everything that you need to run a piece of software or workflow is in one object. It's reproducible. So if you make a container, you can make an instance of it and it should run the same across any instance when you start it up because it has all the same things in it. You can tag and version them so you can build multiple types of containers and give them different versions. So you can go back to older versions if you want. And they're also portable, like I said. They run in any runtime environment. So you can have them on the desktop, the cloud, high performance computing cluster. They run all over the place. So now we get down to the workflow here. So both Ryan and Matt, I think, have introduced the rainfall mapping workflow. And so there's all these different steps that have to happen. So there's all these pieces of software and data that make that possible. So when doing development on this, we have some virtual machines that we set up in the Jetstream NSF cloud to be able to develop and do some of this work. That's one environment that this stuff will run in. You run this workflow and then you manually upload these products to a server or publication endpoint. You can try and automate some of this with some cron for pulling data and trying to do some of that. But when we develop it on one machine, a lot of times it's difficult to move that somewhere else, scale it somewhere else. And so if building a service like this, we wanted to make sure that we could scale and do that. So that's why we containerized all this. So we took all of the dependencies here, stuck it in a Docker container. Now we have a self-contained environment that we can run the daily rainfall, the temperature rainfall, the monthly rainfall, separating these things out into smaller steps if you want, like pulling data from the National Weather Service, pulling data from MADIS, those sorts of things. We can keep making different containers and things like that for that. And we can publish these to container repositories so that we can pull the versions down. Other people can access our software. We can then put these things in like our Jetstream cloud that the NSF funds, or in Tapis. Tapis has a framework for actually running containers as well. So the container sort of workflow development cycle here is we sort of, define what our container environment is going to be. It's basically like a file. You say, it would be like a series of commands like you would normally do if you were going to install a bunch of packages on your own computer, but we write a file so that we know exactly what we're doing, and then the container builds it, puts it on the repository, and then we can register that with Tapis using things like Jupyter Notebooks with the Python SDK that we have. We can run those in some of the cloud instances we have, and just kind of develop and test running these things on Tapis and pushing data in and out of the Climate Data Portal and the EKY Gateway here. So automating this with Tapis. So as we talked about, we build this container, it has all of our things, we register it with our Tapis platform that can run the containers. We can set up actually a cron that can run for individual containers so they can kick off at specific times. So like for daily or monthly or post-monthly for generating those different types of data that we need to do. Tapis will execute our container for us. Our container runs using Tapis's file APIs. It can pull data from the Climate Data Portal. If we need yesterday's data to know something about today, or if we're doing monthly maps, we need to pull the entire last month into our environment and to do compute on. We fetch daily data from other providers. We do all generate our data products, and then we upload those back to the Climate Data Portal, and then we add annotations so that they can be available in our visualizations, and they can be available for our download, as well as folks that are the consumers of these data products know what they are. Finally, some other stuff about some of the infrastructure that we built for the Climate Data Portal. So we tried to make it easier to publish or make updates to some of these codes. So Keri and Matt, they've been writing codes in Python and R. And so we have some Git repositories that they can develop their code, make new changes, push them to this, and then automatically a container will be built and submitted to Docker Hub. And then Tapis has some workflow containers that are checking for updates, and then we'll update the workflows for us. So that's something that Michael Dodge has been working on. Pretty neat. Okay, so now on to the visualization and sort of our data dissemination, data download things. So Jared did a really good job doing some demos here. The whole user interface is powered by Tapis for our backend APIs for where it fetches its data from. And then we built the UI on Angular. Leaflet is the mapping tool that is used for taking gridded map data, showing it here, plotting all the stations and things like that. And then we have some Node.js stuff for some data download as well. So thanks again, Jared, for all the hard work for doing this. He's put in a lot of time and effort on getting that up. So as we're talking about Tapis as a backend, the metadata API is one of the things that we leverage heavily for the visualization component and the data component, because this stores all the information about the stations. We convert time series into these JSON documents. So I mentioned the JSON format earlier. We convert some CSV files into that, as well as file and metadata records to record all the GeoTIFF gridded data that we have access to. And then that way, the selection interface that Jared showed you for being able to navigate and pick rainfall, temperature, monthly, daily, all those sorts of things are dynamically populated from the information stored in that JSON record database. And then you can essentially build the query for what the data is that you want to view in there, or you're building the query for what you're going to export. The way it sort of works for the GeoTIFF files that are generated by the map workflows is they're stored in the Climate Data Portal, and they're indexed with those metadata documents that I'm talking about. So when you as a user define that sort of query in that last interface here, Essentially what's happening is the client that you're using, the Climate Data Portal, sends those REST requests to TAPIS. TAPIS processes those response back by sending the GeoTIFF back to your browser. And then the Climate Data Portal converts that GeoTIFF into the information, the layers that in Leaflet. And Jared actually built some custom parsing stuff to be more performant than some of the other ones that were plugins for Leaflet. And so he'll probably be sharing that out at some point. More stuff here. So for the plotting functions of the time series data, again, that's represented as JSON in the back end. And so we have these JSON records, which represent, like, here's a station that has some piece of rainfall data for the month of December. And this was the amount of rainfall for the month in, I don't think I think this is in millimeters, the values on here, but this is just an example. But essentially this format allows us to add any number of different variable types. So temperature, I think humidity or other things are going to be added later, but we can represent that in this similar format. And then the interface will be able to interpret it and do additional plots and things on new data as we add it into the system. So finally, the downloaded data. So Jared showed this nice interface for building these queries for the different packages of data that you want to build. Again, that's all represented by our metadata service that has those JSON representations of what are the different files that we have access to populate your query interface. You build one of those, you send your selection over REST to the backend. It then decides, what are all the files that you requested based off of your query, puts the package together, and then either sends it to the interface here or it sends you an email. So just kind of wrapping up here, we're going to continue to evolve on the interface and the technologies that power the Climate Data Portal. But just remember that it's TAPIS plus leveraging the old EKY, and then that huge technology system is where the Climate Data Portal is equal to. So with that, you can follow the Climate Data Portal on all the social media stuff that Ryan mentioned earlier. If you have questions or you want information about APIs, you can email me at seanbc@hawaii.edu. And again, just acknowledge the funding from the Hawaii EPSCoR and the National Science Foundation for the Track 1, as well as the TAPIS project. So thank you.
Well, that concludes our technical presentations. I am happy to see 122 people still here after the technical talks. Really awesome job, everybody. All the presenters today, I want to thank them and thank everybody for being here. I think we're at a point now where most of the questions in the chat have been answered. If you want to turn your cameras on and give a comment or have a question, we can just open the floor up. We still have a few minutes left to our official end date, but I think folks are willing to hang out for a few minutes if there's some questions or some comments. You can't throw fruit at us virtually, so I think we're safe on that front. So again, thanks for being here today. If you have some questions, please turn your mic on or put them in the chat. Thank you. Maybe Tom, do you have any closing remarks or anything you want to say?
Yeah, while people are thinking of something to say or ask, I will just say I want to thank Ryan Longman for keeping us all coordinated and organized and on track and pushing us to get things done on time. And yeah, we wouldn't have gotten here anywhere near here without him. And I want to thank all the presenters who did a great job and for all the work that they did that went into what they presented. And a lot of people in the background who, are not out, out in front here, but are very important as well. I would particularly mention Michelle Choi, who is really important to any of these events. We wouldn't think of trying to pull off an event like this without her. So she always figures out how to make it work. So thank you, Michelle. So we'll just turn it back to anyone else who has a question or comment. Back to you, Ryan.
Yeah, I'm seeing a lot of nice comments in the chat here. Is there any thought to integrating underground station data into your database in the future? And the answer to that is if it's available through an API, we're able to access it online, we can do that. We do find some problems with citizen science stations, maybe skipping the weekend and different things. So, if somebody's really rigorous and we can confirm the actual what goes into the data, we can get the metadata, then we can consider bringing that in. But some of these manually read gauges do propose problems sometimes in the data set. So the telemetered stuff is probably in the future where we're moving in that direction. There's a question for Sean in the chat also. Do you see that, Sean?
Yeah, I was talking to, yeah, Jim, you can send data from your instrument to TAPIS, depending on where you want to store it. We do have a new streaming API for doing that, where you can pass in data with just posts and send it in. And we have some other things that you can set some threshold alerts and some other neat things. So yeah, let me know if you're interested on more info.
Great, thanks, Sean.
I think we can probably wrap it up. I'll just say, again, thank you very much. Mahalo to everyone, and leave the last word to Ryan.
Yeah, the last word is we're just getting started, and thanks for being here today. If we can use this email listserv and our social media to keep you up to date when new products come online, and we're actually looking for your help to populate the HCDP2 with research highlights and social media content and your publications and things like that. So feel free to use it and to interact with it and to let us know how we can make it better. And we're here to provide back that data back to the community so that we can do the things we need to adapt to climate change in the future. So getting that data available is a big first step to that. So anyway, thanks for being here today, and we'll see you down the road. Mahalo.